Okay, so welcome back. Let's do Bernoulli's equation now. Let me get my eraser. And let's remember this equation here. The flow rate is constant. A1 V1 equals to A2 V2. Okay. Let's see here. So equation. So the fluid is moving now. You cannot apply, for example, Archimedes. It assumed hydrostatic equilibrium. So here is our pipe, and here is the fluid. On this end of the pipe, you got area 1, and the speed is V1 as it enters this way. And then when it leaves on this end, it is area 2, and the speed is V2, like so. And let's say I'm going to take this one as height 1, and here, from here to here is Y2. Y2. Actually, I mean, assuming I'm taking, here is the ground. So this is Y2, and this is Y1. And I'm going to use the work energy theorem. So who is doing work on this fluid? Well, there are forces on it. There is the force of gravity doing work. And then there is the force of, so who is pushing the fluid? The fluid behind it. So there is pressure here on this fluid, pressure 1, and it's this way. So it's being pushed by the, remember, fluid behind it pushes it this way, And then our fluid here, I'm taking this piece of fluid, by the way. I'm taking this piece of fluid, and I want to know, I want to study it. The fluid here pushes the fluid in front of it, so it gets pushed back, and the pressure here would be P2. So the force there would be F2 times the area, but it's in the backward direction, and here the P1 times the area, and it's in the forward direction. So let's see what the work done by this force here as the fluid moves, an amount delta x. Delta x, let's call it delta x1, and it's equal to V1 times delta t. All right, V1 times delta t, and see what happens. So the work done, I will call it W1 by P1, will be F1 times delta x1, and that is P1 area 1, because force is pressure times area, times V1 times delta t. Okay. And then the work done by the second force upstairs there, it's pressure, but it's backward. So as the fluid moves forward, this force does negative work because the force is this way and the motion is that way. So this is delta x2, and delta x2 will equal to V2 times the amount of time delta t. So it would be negative F2 delta x2, and it is equal to what? Pressure 2 area 2 V2 times delta t, negative sign. Okay, that's good. Now, how much work was done by gravity? Remember, the work done by gravity will equal to the negative of the change in potential energy. So how much work was done? Well, if you take a mass m, if it moved from an amount of mass m, delta m, by how much did the potential energy change? Well, the fluid moved a little bit here and here, so the amount of mass, you can think of it as one piece of mass went from here all the way there. By how much did the energy change? Well, the potential energy has changed by, let me read it here. The work done by gravity will equal to negative the change in potential energy. Okay? Remember, when gravity does negative work, the potential energy change is positive. Right? For example, if I lift this pan, as I lift it, gravity is downward, so gravity is doing negative work, and so the work done is, the change in potential energy is positive. When I let the pen drop, the change in potential energy will be negative, but the work done by gravity will be positive. So you get that. So this will be negative. The amount of mass, let me call it, how much mass do we have? It's delta, let me call it just delta M, a mass times gravity, and then times, if this is y1 and that's y2, would be y2 minus y1. And the change, the amount of mass, delta M, is the amount of mass contained here, which is negative, it would be the density times the volume. So it would be the density of the fluid times the volume. And the volume is the cross-sectional area, area A times delta x1. So it would be area A1 delta x1. That's how much mass is there. You might ask, why didn't I use the density times area 2 times delta x2? The answer is we could. And they're exactly the same, but remember the equation of continuity. The volume flow rate is the same. And what is delta x1? It is, so I have negative rho A1. Let me make sure. Density times A1. So that's the volume. Oh, I forgot the G and the Y2 minus Y1. Yeah. So let me erase this. So let's see. I have negative. Delta M will be rho area 1 delta x1. So that's the delta M part times G, and then times y2 minus y1. And what do we get here? Delta x1 is v1 delta t. Okay, so I have the work done by gravity, therefore, will be negative rho a1 v1 delta t, and then times g, and then y2 minus y1. Okay, so there is work done by force 1, by force 2, and by gravity. And remember, the work done is equal to the change in kinetic energy. Change in kinetic energy. So we'll use the work energy theorem. The work done will equal to the change in kinetic energy. Okay. So what do we get? Total work done will be, I'm going to put this and this and this together. So P1 A1 V1 delta T, and then minus P2 A2 V2 delta T, minus, this is the work done, minus rho A1 V1 delta T times G times y2 minus y1 will equal to the change in kinetic energy. Will equal to the change in kinetic energy. And what is the change in kinetic energy? Let me first, let's keep it this way first. Change in kinetic energy. Okay, for now. Now, A1 V1 delta T, that is the volume flow rate times time, times an amount delta T. Remember when we had Q was equal to A1 V1 and it's equal to A2 V2. So A1 V1 times delta T will equal to A2 V2 times that same amount of delta T. So A1 V1 delta T, A2 V2 delta T, A1 V1 delta T, they're all A1 V1 delta T if I like. I can call them A1 V1 delta T. So I'm going to factor that. So I have A1 V1 delta T times what? Now I have pressure 1 minus pressure 2, that's what's left, and then minus rho G, and then here y2 minus y1, like so, equals to the change in kinetic energy. Let's write down what's the change in kinetic energy. Let me do it here. The kinetic energy at this step, it's this mass and how fast it was moving, so it is 1/2 delta M times V1 squared. And remember what delta M was. Delta M was rho A1 delta X1, which was rho A1 V1 delta T. So it was 1/2 rho A1 V1 delta T and then V1 squared. Okay? And then the kinetic energy at the top will be 1/2 delta M V2 squared. And you see delta M and delta M are the same. So instead of delta M, I will just write 1/2 rho A1 V1 delta T and then times V2 squared. So it will be 1/2 rho A1 V1 delta T. We could have written it as A2 V2 delta T, but they're exactly the same quantity by continuity. V2 squared. So the change in kinetic energy K2 minus K1 will be these two minus each other. So K2 minus K1 is equal to the change in kinetic energy equal. So you see 1/2 rho and this stuff, they just factor. So 1/2 rho and then A1 V1 delta T and then I have V2 squared minus V1 squared. So I'm going to write it here. That's for the change in kinetic energy. 1/2 rho A1 V1 delta T and then V2 squared minus V1 squared, like so. Well, here is why I factored them. This and this cancels. All that stuff cancels. And so let's write this one more time. So I have P1 minus P2 and then minus rho G Y2 minus rho G Y2 and then minus times minus is plus rho G Y1 equals to 1/2 rho V2 squared and then minus 1/2 rho V1 squared. So now everything that has a 1 I will put on one side and everything that has a 2 I'll put on one side. So I have P1 plus rho GH1, I'll put plus 1/2 rho V1 squared plus rho GY1 will equal to, move the pressure there, get P2 plus 1/2 rho V2 squared and then plus rho GY2. That's called Bernoulli's equation. All right, it's kind of a mouthful. It's a long equation. Now I led you through the derivation, but all you need to know is really this equation here, and this is the logic where it came from. Okay, I can explain it further during the discussion. I know I went through it a little bit quick for the sake of time, but I can do it more carefully or more slowly if you want. Just ask me. Good. Took 13 minutes. So I'm going to erase this board and just write that equation and then try to apply it to a couple of problems. So we have two equations. This is continuity and Bernoulli's equation. So let's see. So you can't go back to now Newton's laws every single time and go all the way back, because you have to go through this derivation each and every time you try to treat fluid dynamics. You don't want to do that, so we would just, it's a summary of it's a result, and so it's worth having or remembering or writing down. So we have two equations. We have the continuity A1 V1 equals to A2 V2. This is conservation of mass basically. And we have Bernoulli's equation that says P1 plus 1/2 rho V1 squared plus rho GY1 will equal to P2 plus 1/2 rho V2 squared plus rho GY2. When can you apply it? Whenever the fluid is moving at without turbulence and no friction and so on. So it's an ideal fluid. So I'm going to now look at an example here. All right, so here is the example. We have a as usual, a pipe that flows, that has fluid flowing within the pipe. And I'm going to choose this. So you get Y2 here is 2 meters. Y1 will be 0. I'm just choosing the bottom here as the reference. 2 meters. And the pipe at the bottom has a diameter of 6 centimeters. Diameter here. Diameter 1 is 6 centimeters. And the diameter here, let me write it down. It is 4 centimeters. 4 centimeters. The fluid here is coming in with a speed v equals to 4 meters per second, I think, or 5, one of them. Actually 5. 5 meters per second, yeah. V1 is 5 meters per second. And we're given the pressure here. We have a gauge that reads the pressure, and P1, right? We can measure pressure. P1 is 75 kilopascals. 75 kilopascals. That's 7.5 times 10 to the 4 pascals, or newtons per square meter. And the question would be, V2 here will equal to what? And what is the pressure at the top here? How much is it? What's the pressure there? Okay. So this is our friend. You see here, we have area 1, V1, and we have area 2 over there. We have the diameter, so we could get the area. And we're assuming it's a circular cross-section, by the way. So we could get V2. So for part A, let's do V2 first. So we have area 1 V1 equals to area 2 V2. Area 1 is pi r1 squared. So that's pi diameter 1 divided by 2, the whole thing squared. And V1 will equal to area 2, that's pi r2 squared. That's diameter 2 divided by 2. And the whole thing squared times V2. And you see the pi here cancels, and the 1/2 when you square it, it becomes a 4th, so the 4th cancels on both sides. So you have basically diameter 1 squared V1 will equal to diameter 2 squared V2. And this happens so often, you can just remember it. It's just diameter squared, because the area is proportional to the diameter squared, so this happens very often. So you get V2 will equal to diameter 1 divided by diameter 2, the whole thing squared, times V1, and let's see, diameter 1 is 6, diameter 2 is 4, so we have 6 over 4, again the centimeters cancels anyways, and then times V1, which is 5, and so we get V2, let me get my calculator, where is it at? Basically we get 11.25 meters per second. So 11.25 meters per second. So that's V2. And now pressure 2. The only thing in town that tells me what the pressure is this equation. So I'm going to use it. So I know that, so for part B, pressure 1 plus 1/2 rho V1 squared plus rho G Y1 will equal to pressure 2 plus 1/2 rho V2 squared plus rho G Y2. I want pressure 2, so pressure 2 will equal to move everything else to the other side except for pressure 2. So you get will be pressure 1 plus 1/2 rho V1 squared minus V2 squared. So when you move this to the other side, factor the 1/2 rho, and you end up with this. And then plus rho G, and then Y1 minus Y2. And minus Y2, like so. And plug in the numbers. P2 would be 75 kilopascals. So 75 times 10 to the 3 plus 1/2. The density is water that's flowing, so that's 10 to the 3. And then V1 squared minus V2 squared. V1 is, what was V1? It was 5, so 5 squared. Minus V2 squared, that's 11.25 squared. And then plus, so this will be a negative quantity. And this will also be negative here. Rho is, again, 10 to the 3. G is 9.8. Y1, the height at the beginning is 0. Y2 is 2. And so P2, you see everything has 10 to the 3, so we will just have an answer in kilo pascals. And let's plug in the numbers and get that number. So you get basically 4.6, about 4.6 kilopascals. Okay, approximately 4.6 kilopascals. So it went from 75 to 4.6 kilopascals, which makes sense. When you go upstairs, you barely have any pressure. You need like a pump or something to get the water up. And this brings me to something. I actually made a mistake here. Not really made a mistake. The numbers will still be the same, but this one here is called the pressure here. They gave us what's called the gauge pressure. The gauge pressure is how much more than the atmospheric pressure it is. So P gauge will be whatever your pressure is, the absolute pressure, basically how hard are the molecules hitting one another, minus P atmospheric. So in our case, they say the gauge pressure is 75 kilopascals, but the absolute pressure will be, if you move the atmospheric pressure to this side, you will get, atmospheric pressure is what? P atmosphere is 1.01 times 10 to the 5th pascals. We can change this to 101 times 10 to the 3 pascals, which is 101 kilopascals. So the absolute pressure is really, in this case, it would be 75 plus 101 kilopascals. And at the bottom here, the absolute pressure will be 4.6 plus the 101 kilopascals. I forgot to mention the concept of the absolute pressure and the gauge pressure. The gauge pressure is like if you have an empty or a flat tire. The good news is that the pressure inside the tire and the pressure outside are the same. So the pressure inside the tire is 1 atmosphere. The bad news is that's not good enough to drive. You need the pressure inside the tire to be higher than the atmospheric pressure for you to be able to move. I will end this video with another example, and then we will do probably 2 or 3 more in Bernoulli's principle, and then we'll move to the last section of this. So let me do one more conceptual example here. Okay. Let's see here. I need to get a new eraser. This one's becoming. Okay. So imagine you have a really large tank here. Okay, a really large tank here. Let's say a reservoir of, and it has milk, right? The reason I remembered milk because of this current pandemic situation. We had people, remember, they disposed of milk because they had no one to buy it. And so anyways, it could be water, it could be milk, it could be whatever. So you have to drain this thing. You have to drain the water here. So let's say this is like 1,000 gallons or maybe 2,000 gallon container, a large container, maybe 1,000 gallons. It's a 1,000 gallon container and you're draining it here. The fluid here barely has any speed. So you see it's similar to the earlier situation. You have fluid here coming out from here. In here, we just have it reversed. We have the fluid here coming out from here. even though it doesn't look like a nice curvy pipe, but it's this fluid draining. So you will have the following. The fluid will come out here at speed V2, and the fluid here might have speed V1. The fluid here might be dropping at a speed V1. The pressure here, P1 is just, it's open to the atmosphere, so it's P atmospheric. So it is the atmospheric pressure. And here also, if you look at, here's the fluid before, let's say the moment it starts to flow, it is the atmosphere here. So the fluid will come out, and P2 is also P atmospheric. Okay? And let's say here is Y2 equal to 0, and Y1 is equal to the height. So we're going to use Bernoulli's equation, which says P1 plus 1/2 rho V1 squared plus rho GH1 or GY1, and that equals to P2 plus 1/2 rho V2 squared plus rho GH/GY2. P1, P2 both are atmospheric pressure, so that cancels. Y2 is at the bottom, so that's a 0. Now, we have to make one more assumption here. V1 is approximately 0. As you open the faucet, this thing drains. Yeah, it falls, but like a couple millimeters per second, whereas this one is flowing at meters per second. So it's much, much less. So this is approximately 0, really, really close to 0. So I'm going to just throw it away. So you get rho GY1 is equal to 1/2 rho V2 squared, and you get rho cancels, and you get V2 will equal to 2GY1 square root. Compare this to the following. Let's say Y1 is H, and then Y2 is 0, and V initial is equal to 0, and something is falling under the influence of gravity. And we know from kinematics that Y final equals to Y initial, we'll use the other equation, V final squared minus V initial squared is equal to, so since we're calling it 1 and 2, so V2 squared minus V1 squared is equal to minus 2GH, which here you have Y2 minus Y1. And if the initial velocity is 0, you get V2 squared is equal to minus 2G times Y2 is 0 minus Y1. Minus times minus is plus, so you get V2 will equal to 2G Y1. So that's the speed. So it's as if one drop of water comes out, drops from here all the way to the bottom and falls, and that would be the speed of it. And Bernoulli's equation, it comes out of it. If the water can fall appreciably large, then you cannot ignore this term, and you actually have to solve for it. And the way you solve for it is you say, by continuity, if you know the diameter of this drain and the diameter here, you can use continuity A1 V1 equals to A2 V2 and solve that way. Okay. The algebra will be messier. So I will stop this one here, and then I will see you later for the next video, where we do some more examples of Bernoulli's principle, and then the last section, Young's modulus and elasticity. And then we will do practice problems of the end of the chapter. Okay, I'll see you.